Okay, good morning everybody. Yeah, am I audible?
Good morning, sir.
Good morning. Shall we start? Only 12 members are there. 40 members are there. Okay, yeah, first unit has been completed. I will quickly revise the first unit and then we will do some problems. Right. So in the Teams, I have uploaded all the material. You can see from the Teams. In the master answer one, this is a diffusion PPT is there.
Sir, can you give presenter permission, sir?
Means I have
Like,
to give.
no, 2 members of my friends are requesting to invite them, sir. That's why.
Okay, now also invitation is needed.
From mobile, some network issues, sir. That way, I think.
Okay, I said.
Thank you, sir.
Yeah. Yeah, you can see from the teams in the left side every channel is there. In the mass transfer one, when we click this one and go to the files, you can see the first one is a PPT, MTO1 unit 1 PPT. Diffusion is a chapter's name or a unit name. Then this is MTO1 unit 1 problems. Okay, every problem, around 21 problems are there. I have solved and given to you. Then this is a unit 1 notes, complete notes. Then the second unit also I uploaded the notes. You can go through that one also. Okay, here unit 2 is there. Yeah, the unit 2 also I have day. In the next day, another day, we will start this unit 2 distillation, which is okay. Then the last class was regarding this discussion wetted wall tower, how we derive these equations and everything. We are just considering, because this is a counter current flow. We are considering the logarithmic mean values of uh, pressure or this one concentrations, mole fractions. Now we'll quickly revise this unit 1. Okay, yeah. Unit 1 is the diffusion, regarding everything about only diffusion. This is the basic unit. Okay, how diffusion is taking place. As you can see here, the colors are being dissolved. Here the yellow color and this is the blue color. Blue color are just dissolving in the water. How this dissolution process will take place? Because of diffusion only. Diffusion of this coloring compound, which is present in some solid particles. So it is just dissolving in this water. Now in the gases phase also, see, when the pressure is very high, the gases are just remaining, more gases particles are remaining here. When the pressure we reduce, because low pressures favors the diffusion process, so the particles of gases are moving towards the vacuum. So similar is the case in the solids also. In solids we are just mixing with each other. The diffusion only will takes place. In the liquids also the diffusion will takes place. Here the dissolution process, the solid particles are just dissolving in the liquid. All are nothing but examples of diffusion. Okay, some solvent is there. In some solvent, the solid particles are just getting dissolved. Is nothing but a diffusion. So unit 1 contents of the like this introduction. Okay, just what is diffusion, what are the examples of various diffusion processes for gases and liquids. We will discuss in we have discussed in the introduction chapter. Then fixed first law of diffusion. We know what is fixed first law of diffusion. Ja is equal to minus dab dou Ca by dou Z, where Ja is the flux with respect to any, and minus sign signifies the, and minus sign in the fixed first law of diffusion signifies that the concentration is varying from higher concentration to lower concentration. Then dou Ca by dou Z is nothing but a concentration gradient or a driving force we can call. The next one we have to see the continuity. We have already seen the continuity equation. How we can derive the continuity equation: dou ux by dou x plus dou uz by dou uy by dou y, dou plus dou uz by dou z is equal to 0. This is the continuity equation for the three dimensional. For the three dimension, we have just derived that one. Then the next one is molecular diffusion. Okay, there are two types of diffusions. One is a molecular diffusion and another one is a eddy diffusion. Molecular diffusion in the laminar flow, we will just discuss regarding this molecular diffusion. And there are two cases, okay, two major cases in this one. One is the molecular diffusion in gases and another one is the molecular diffusion in liquids. Among these two cases, there are further two cases are there. In the gases itself, there are two cases like A through non-diffusing B and equimolar counter diffusion case. Similarly, for the liquids also, A through non-diffusing B and equimolar counter diffusion. These are the overall, when we combine, these are the two major cases, and the sub cases, including all the sub cases, there are four sub cases for this one. So for each one we have a derivation, lengthy derivation. Only A through non-diffusing B in liquids will have a lengthy derivation, When you understand this A through non-diffusing field for liquids, you can understand all the remaining three derivations easily. Okay, then next one is the mass transfer in turbulent and laminar flow. Okay. Usually every mass transfer operation will have more than one phase. So for the more than one phase, this is very convenient to evaluate the mass transfer coefficients. Okay, it will give a diffusion rates and everything. So mass transfer coefficients are the usual criteria which is applied to determine the mass transfer in laminar flow and turbulent flow. Okay, whereas where there is a convection of a mass, okay, similar to the heat transfer, where there is a conduction. Okay, then we will use the Fourier's law of heat transfer. Where there is a convection, we will use the Newton's law of cooling. Okay, similarly here also for the conduction case, you can refer to this as a conduction mass transfer case. For the conduction mass transfer case, we can have a fixed first law of diffusion. Governing law is fixed first law of diffusion. Whereas for convective mass transfer, so we need to have a mass transfer coefficient. Okay, when more than one phase is present, so mass transfer coefficients are very convenient criteria to express our mass transfer process. So for the mass transfer processes, how this mass transfer coefficients will be estimated, how the mass transfer is taking place, to explain that phenomena, there are many theories like two film theory, penetration theory, surface renewal theory, surface stretch theory, film theory, and boundary layer theory. These are the theories, various theories are there. Out of all these theories, only four theories are relevant to your context. One is the film theory. So extension of this film theory is nothing but a two film theory. Then next one is a penetration theory. Then surface renewal theory. Then the last one in this unit is the estimation of mass transfer coefficient using a wetted wall tower. So a wetted wall tower is nothing but an experimental setup through which the mass transfer coefficient to the falling film, okay, falling film through which the gas is passed, then its mass transfer coefficient can be estimated. Okay, this is used in the laboratory scale or the pilot scale plant to estimate the mass transfer coefficient of a particular gas or liquid. Then what is mass transfer? Okay, mass transfer is nothing but a migration of species from higher concentration level to the lower concentration level. Okay, this is nothing but a mass transfer. Similar to heat transfer, we can assume the transfer of heat from higher temperature region to lower temperature region. Mass, because this is a mass transfer course, so here mass is being transferred. Okay, then the mass transfer process is a complex phenomenon. Why? Because due to diffusion is also taking place, due to the bulk transfer, due to the convection transfer, all the transfer will be involved, all the three-dimensional. It is a three-dimensional view, mass transfer. Mass cannot be transferred in only one direction. Okay, usually for our convenience of solutions, we are adopting only single dimension, but mass can vary in all the three directions. So this is a complex process. Then occurs through different mechanisms. Okay, that's what we are referring. The mechanisms like molecular diffusion or the bulk or convection transport also it can be possible, and turbulent mixing with some agitation. When we provide some agitation, it is nothing but a turbulent mixing. So that is nothing but causing a eddy diffusion. So eddies will form, some packets of eddies will form. Then packets of eddies will be responsible for dissolving that particular solids into that solvent. So that is called a turbulent mixing process. As you can see here, the diffusion is the main criteria in which governs the mass transfer process. So which is the main mechanism to which governs the mass transfer process. Then what is a diffusion? Okay, diffusion is nothing but a transfer of that particular component from one region, nothing but a higher concentration region to the lower concentration region. Then there are two types of diffusions. So one is a molecular diffusion, which usually takes place when the random velocities. Okay, the molecules are moving with some random velocities, and at the same time it is occurs in a laminar flow. Okay, without any the particle to particle distance, the mean particle distance between the one particle to other particle will be very high compared to the case of eddy diffusion. So when there is no much interaction between the particles. Okay, when there is a much tight packing between the particles and particles, then the diffusion takes place is called a eddy diffusion. It occurs due to the circulatory or eddy currents, or some packets will be formed in that one. So that packets will be responsible in order to get that diffusion process, get through that diffusion process. The example for diffusion, molecular diffusion and eddy diffusion is just dissolve some salt in water. Okay, to occur this process naturally or with a molecular diffusion, it will take some time. Okay, very much time. Whereas when we provide some agitation, when we just stir it with spoon, the salt is stirred with the spoon, the diffusion process or the dissolution process or the salt mixing process takes a very less time compared to the molecular diffusion process. This is the clear example for the molecular diffusion and anti-diffusion. When some external force we have applied, then the diffusion process will take place very much speed. The process will be very much speed up. So that process is called the eddy diffusion process. So there are various types of mass transfer operations. All this diffusion process, convective, bulk transfer, yeah, industrially there are many processes which found interest in very mass transfer operations. Like the first one among those is absorption. Absorption is nothing but a transfer of solute from the gas phase to the surrounding solvent, to the counter currently flowing solvent. Solvent is nothing but liquid. So this operation is referred to as gas to liquid operation. Then the examples for this is absorption of NH3 in water is the clear example of this absorption process. Okay, then next one is the extraction. So usually the extraction process in the industrial terminology, it is referred to as liquid extraction, because this is referred only the transfer solute. Extraction process. Therefore, this is a liquid extraction process. Then the next one is the extraction. For the extraction, we can say some fermentation growths will be extracted. Okay, in the pharmaceutical industries or in some sugar industries, the extraction process will take place. This is the example. Then next one is a leaching. Okay, leaching is nothing but a transfer of solute from a solid phase to the liquid phase. Okay, so this operation is from solid phase to liquid phase. The examples for this is the oil extraction, extraction of oil from the oil seeds. Okay, because oil is present inside the seeds, oil is nothing but a solute. So that solute is dissolved in the surrounding solvent. Solvent is in liquid phase. And another one for the liquid leaching is tea preparation process. The solute which is present inside the tea particles, just we are extracting that with a hot water. Okay, so that is a leaching process. Then adsorption process. Okay, adsorption process is transfer of solute from the fluid phase. Fluid may be liquid or gas, from the fluid phase to the solid phase or to the surface of the solid. Okay, in catalysis there is a much application in the adsorption application is very much in the heterogeneous catalysis. So that is the example for the adsorption process. Okay, then next one is membrane separation. Okay, we are having in our college we are having a in which whatever the particles which pass through that particular membrane is called a permeate. Whatever the particles which are retained on that particular membrane surface is called a retentate. So there are two outputs for the membrane separation. One is a permeate and the next one is the retentate. So RO, reverse osmosis, is the clear example of this membrane separation. Then humidification. What is humidification? Humidification is nothing but a transfer of water vapors to the surrounding gas is nothing but a humidification. So water may be in the liquid phase, so that water needs to be get down into the surrounding gas phase. So this is a liquid to vapor operation. Then evaporation is nothing but a removal of relatively large amount of water from the solid particles or some liquid particles in order to concentrate them. So that is nothing but a evaporation operation. So concentration of juices, okay, by evaporating the excess amount of water which is present uh, in that juice composition is nothing but a example for evaporation operation. Then crystallization. Crystallization is nothing but a mass simultaneous mass and heat transfer operation by which the particular solution will be heated up to its saturation point, up to its super saturation point. Therefore, when they are reaching up to its super saturation point, what will happen? That particular solution will convert into a form of solids. So that is nothing but a crystals. It will convert into the crystals. So clear example for this one is the sugar preparation. Okay, in the sugar industry, the crystallization setup is the heart of that sugar industry, because after extracting the sugarcane juice, whatever the sugarcane juice is, needs to be concentrated with certain triple effect evaporators or multiple effect evaporators. Then it will be sent to the final unit called a crystallization unit. What will happen there? It will be heated up to the saturation limits, up to a super saturation, or just forms a solid. And then drying. Drying is nothing but a removal of very small amounts of water present in the interstices of the solid particles. So drying, in the catalysis, drying will have many application in seeds drying process, in the grain drying process. Everything okay requires a this drying process. Spray dryer, okay, in order to prepare a powder from the milk. Okay, the dryer used is called a spray dryer. Okay, because when we spray that particular liquid at a high temperature, so what will happen? That particular liquid will form a powder. So milk powder preparation from the milk is nothing but a drying operation, spray drying operation. This is the example for the drying operation. Then next one, last one is the distillation process. So in the distillation process is nothing but separation of a constituents compounds based on their relative volatility or based on their boiling points. Okay, when the volatility of a particular component, say A is high, the first component which is going to get as a product is A, because its volatility is very low, because its boiling point is also very low. Okay, so because of this difference in boiling point, that particular constituent compounds will be breakdown. That is called a distillation. When this operation is carried out in a batch process, this is called a distillation. When this operation is carried out in a continuous fashion, that operation is called a fractionation. Okay, so distillation will when simply we can say it is nothing but a batch distillation. When it is carried out in a continuous fashion, this is called a um, fractionation. So you will see in the next two chapters, next two units, unit 2 and unit 3 is regarding about distillation. Okay, unit 4 is about leaching and unit 5 is about extraction. All other operations like adsorption, membrane separation, humidification, these all things you will see in the mass transfer 2. Probably we will undergo in the next semester. Then the next topic is the fixed first law of diffusion. Then what is fixed first law of diffusion? Governing equation in the mass transfer operation, as like to that of Fourier's law of heat transfer in the heat transfer course. This is same as that of the equation. So Fick's first law of diffusion is nothing but a flux is directly proportional to the concentration gradient. Ja is directly proportional to minus dou Ca by dou Z. Okay, the proportionality constant in this Fick's first law of diffusion is dAB, where Ja is the mass flux of component A. So its units will be mole per meter square second. So dou Ca by dou Z is nothing but a concentration gradient or a driving force. So whose units are mole per meter power 4. Okay, why mole per meter power 4? Because concentration is mole per meter cube and Z is there. That Z accounts for 1 meter. So mole per meter power 4. So Ca is the concentration of component A, whose units are mole per meter cube. Then Z is the distance of diffusion, that particular mass transfer path distance. So which will be measured in meters. So flux, how we can define the flux? Okay, this is nothing but a rate of transfer of species I per unit surface area in the direction normal to the surface. The rate is nothing but mole per second. Rate per unit area is nothing but a flux. Okay, we can define that flux when we know these units of that flux. Okay, rate is mole per second. Rate per unit area is nothing but a flux. So these are the various properties, how to estimate the properties of a mixture. Okay, these are the formulas when we consider some mass. Mass is the basic quantity. So all these are the derived quantities. So out of these basic quantities, we can derive all these quantities. So see mass Ma, Mb for the individual components. So it is additive property. So M is equal to Ma plus Mb. So velocity is a vector, so UA and UB. So we cannot add U is equal to UA plus UB. So we need to specify in which direction that particular velocity is there, because it is a vector. So volume also, volume is indicated with a capital V for the individual component VA, VB. So it is additive property, VA is equal to VA plus VB. So like that you can, as we can derive all these mixture properties. This is called a mixture properties. So when since our mass transfer course is concerned only about two binary system, so binary system means only two components are there. So for the binary systems, all these formulas are applicable. When we have a more than two components, we will add one other component here. So according to your syllabus context, only two components are there, since this is a binary component. So these formulas are frequently used to estimate the mixture properties. Okay, this is also provided in the word file also, so you can choose among them for the liquid and gases what type of formula suits for the particular problem. Then fluxes. Okay, there are two types of fluxes. Okay, one is the flux with respect to some stationary coordinate, which is indicated with Ni. Okay, fixed or stationary, nothing but same. So Ni is nothing but a flux with respect to a stationary coordinate or a fixed reference framework, or Ji. Next one is Ja. Ja is nothing but a flux with respect to some arbitrary framework. So velocity of an observer is also moving with certain velocity, whereas in this type of flux there is no movement of other velocity. Observer velocity is zero. So it is defined with an example that when some sailor is floating just with using its board in the stream, in the water stream, that sailor will have certain velocity, whose velocity is denoted by u naught. Okay, then velocity of that particular species in the control volume will have certain velocity. Thus velocity is known as ui. So the flux with respect to stationary coordinate or some fixed coordinate system is given as Ni in terms of mass is rho I into ui, whereas that flux with respect to moles is given as Ci into ui. So first flux with respect to some arbitrary coordinate system is given as, because why it is arbitrary, because observer is also having certain velocity, he is also moving with certain velocity. That velocity is indicated with u naught. When we define this flux equation in terms of mass, we need to use a rho I. Okay, this is a mass mass concentration. This is a molar concentration. Ca is a molar concentration. Rho I is a mass concentration. So rho I into ui into u naught. So here also Ci into ui minus u naught. So in a different systems we will apply different terminology for this u naught. Then how this u naught is defined? This for defining this u naught, there are three types of criteria. One is we can define it as a mass average velocity. Otherwise, we can define it as a molar average velocity. Otherwise, we can define it as a volume average velocity. So molar average velocity we can define with this equation, because we are considering the mass average velocity. We are yeah, when we use the mole, when we require a mole concentrations or a mole fluxes, you need to use this formula in this equation in place of this u naught. Okay, when we require some volume average quantity, okay, since for the gases volume concentration, volume percentage is equal to mole percentage is equal to pressure percentage. So we can use this formula here also in place of this u naught. You can use this also. So frequently we need to use these two equations, mass and molar average. So in place of this u naught, we will substitute this. In place of this u naught, we will substitute this one. So these are the definitions for the fluxes. So what is the relationship between these two fluxes, Ni and Gi? We need to adopt that one also. So for deriving, so we are assuming this is a steady state processes. Steady state means which is independent of time. So this is the relationship between fluxes. So we have derived this equation. You can refer to the earlier videos. So the equation which we obtain the relationship between fluxes is Ni is equal to Nxi in Nxi plus Ji. So for the component A, when we apply this equation, in place of I, we have to substitute A. So then using the relationship between whatever the fluxes, this relationship between fluxes and the fixed first law of diffusion, we have derived DAB is equal to DBA. We have shown that. Instead we have just proved this one. DAB, diffusivity of A through B is equal to diffusivity of B through A. Okay, this equation we have just proved that. So next one is what is mass balance equation. Okay, mass balance equation is nothing but rate of mass output minus rate of mass input plus rate of accumulation is equal to rate of mass generation inside the system. So this is the mass balance equation. With certain assumptions, we can cancel out the terms. When there is, we can assume that there is no reaction term, we can neglect this generation term. When there is no when the process is at steady state, we can neglect this accumulation term. When the mass balance is applied at without reaction and at steady state, we can neglect these two terms. Then simply the mass balance equation will reduce to output is equal to input, rate of mass output is equal to rate of mass input. Okay, this balance equation we have used to derive the continuity equation. So this is the continuity equation, dou ux by dou a, dou x plus dou uy by dou y plus dou uz by dou z is equal to 0. Then how do we derive this equation? By applying certain assumptions. So what are those assumptions? So those assumptions are nothing but steady state and density is constant, no reaction is there. So next is the assumptions. Assumptions in the Fick's second law of diffusion. So Fick's second law of diffusion is applicable for the unsteady state condition. Unsteady state condition means which is dependent on time. The process is dependent on time. So Fick's first law of diffusion is defined for the unsteady state conditions, whereas Fick's first law of diffusion is defined for the steady state condition. It is a steady state formula, but this equation is the unsteady state formula. So assumptions applied in deriving this equation is velocity is 0 and no reaction is there. So no reaction is there, this term can be cancelled. So velocities are 0, certain variables are cancelled now. So in between the continuity equation, we have derived this equation. You can refer to the earlier videos. So the next cases are steady state molecular diffusion at rest or a laminar flow. So A through non-diffusing B. So for the liquids, whatever the, for liquids or the gases, whatever the steady state molecular diffusion taking place in the A through non-diffusing B, that means sub B is remaining constant, whereas when there is a two components in a mixture, okay, only one component is getting transferred in into that solvent or the into some particular solution of interest. Okay, then the other component will remain as a stagnant. So that case is clearly referred to as A through non-diffusing B. So this is the case. It is a case of diffusion occurs when component A. So in this both cases, NH3 or benzene is diffusing, whereas component B, which is air in this case, and this is in this case also air. These are remaining constant. These are remaining stagnant. So this is the case of A through non-diffusing B. Then the example for non-diffusing B case, the benzene is present in the liquid form. So when surrounding air is just flowing around the tube, flowing around the test tube, what will happen? That air will replace some of the liquid inside this tube. So the transfer of benzene to this surrounding air is the example of A through non-diffusing B, because air B is not at all diffusing, so it is remaining stagnant. Okay, then for the gases phase example, the transfer of NH3 from air and an NH3 mixture to water. So in this case, air and NH3 gas mixture is there, in which NH3 is getting transferred into the liquid phase, which is present in the water. Okay, so here the B, which is air, is also remaining stagnant. It is not at all dissolving in water. So oxygen is very much less soluble in the water compared to the NH3. NH3 is highly soluble in water, so NH3 will just go inside this water. So these are the two cases, two examples for the A through non-diffusing B. So for the liquids, we already know what is the concentration. Concentration is nothing but mole per unit volume. So for the liquids, we usually take the rho by m average, density by molecular weight average, because solutions is always composed of more than one component. So average concentrations we have to consider. So in doing so, using the relationship between diffusivities, which is Na is equal to Nxa plus Ja, and Fick's first law of diffusion is equal to Ja is equal to minus dAB dou Ca by dou Z, with applying Nb is equal to 0, because capital N is equal to Na plus Nb. In that one, when we apply Nb is equal to 0, then N is equal to Na. So when we apply this equation in the relationship between diffusivity together with Fick's first law of diffusion, we can obtain this equation. So when this equation, we just expand C as rho by M average, we can obtain this equation. When we perform certain operations, certain manipulations to this equation, we can obtain this equation in terms of some logarithmic concentration differences. So CBLN is defined in a way that. So earlier we have derived this equation, you can refer to the previous videos. Then in terms of mole fraction, these are in terms of concentration. So in terms of mole fraction is nothing but individual concentration divided by total concentration, or individual moles divided by total moles in the liquid phase. Okay, when in the gas phase, individual pressures divided by total pressures. Okay, to this formula, when we divide with the total concentration, so Cc will be cancelled. Ca1 by C is equal to mole fraction of component A in at point 2. So Xa2 and Xa1. So in terms of mole fraction, these formulas are applicable. Next one is for the gases case. So for the gases, we define concentration. Concentration definition is same, N by V, mole per unit volume. But for the gases, it is usually convenient to measure in terms of partial pressures or the pressures. So since this is the total concentration, we are using the total pressure, PT. This is PT. Okay, we can write this as a PT concentration. Total basis. Since that is a total concentration, we are defining as a PT. Okay, then applying this C is equal to PT by RT, and at the same time the NV is equal to 0 case, because this is A through non-diffusing B in the relationship between diffusivities together with the Fick's first law of diffusion, we have obtained this equation. PT by RT is ln PT minus PA2 by PT minus PA1. Okay, after certain manipulation, after certain manipulations of this equation, we are obtaining this formula. So in which PBLN is nothing but a logarithmic mean pressure differences. So whose expansion formula is given here. So then after converting this PT or PA1, PA2, everything in a mole fraction terms, this is applicable, because PA2 by PT is nothing but a YA2. PA1 by PT is nothing but a YA1. So because these are the expressed in mole fractions, this formula is come from this one. This formula comes from this one. So this is for mole fraction terms, and this is for pressure terms. So then next one is the steady state molecular diffusion case at rest for the equimolar counter diffusion. Then what is the equimolar counter diffusion? Okay, a component A and B is there in some phase. Okay, when A is also competing to get transfer in that particular liquid, and then at the same time B is also getting competing with each other. A is also competing with B, and B is also competing with A. So they will equally compete with each other in order to get diffused in certain composition. So those fluxes are Na is equal to minus Nb, because opposite direction. In the opposite direction, you are getting competition. So that is called, so N is equal to Na plus Nb. When Na is equal to minus Nb, that's simply the total flux is 0. So the first example for this equimolar counter diffusion is the distillation operation. Okay, distillation operation in which the reflux condenser is there at the top of the distillation column. The role of the reflux condenser is part of the vapor, which is part of the vapor which is converted into the liquid will be just sent back to the distillation column in order to enrich the content of more volatile component in the vapor fraction. So the the reflux condenser plays a role in enriching the content of that particular more volatile component in the distillation column. When this is taking place, the component A and B are competing here. So in transferring the masses from to each other. So this is the example for equimolar counter diffusion. And certain other example in the solid phase is the heterogeneous catalysis operation. In the heterogeneous catalysis operation, what will happen? For example, say A plus B gives rise to C, or A plus B gives rise to C plus A. So first A plus B reaction needs to happen on the catalyst surface. For the catalyst, for the reaction to happen on the catalyst surface, first these compounds A and B needs to be diffused inside the catalyst surface. Okay, first resistance is a diffusion resistance, and after that this needs to be adsorbed on the catalyst surface. Okay, on the surface of the catalyst, both are getting adsorbed. So this adsorption will take place at equal rates. Okay, so Na is equal to minus Nb. This is the clear case that so both are competing. A and B are competing to adsorb on the surface of the catalyst. So this is the mass transfer case of equimolar counter diffusion. So after this only, after this adsorption only, the surface reaction will take place. Then the product P will form. So that product P will just diffuse or dissolve or just removed from the catalyst surface. Okay, this is the clear case for the equimolar counter diffusion. So for the liquid, same formula, C is equal to individual mole by unit volume. So for the liquids, rho by m average we define. So this is a simple case. Na is equal to N is equal to Na plus Nb. We can substitute N is equal to 0. Then the relationship between relationship between fluxes will be very easy. So this is the easy integration formula. So it is a very small flux formula. So in terms of concentration, we need to express this one. When we convert this formula into mole fractions, we need to obtain this equation. So similarly, in place of C, we are substituting rho by m average. So similarly, for the gases, we already know C is equal to P by RT from the ideal gas law. So after substituting in the relationship between fluxes and Fick's first law of diffusion, we can obtain this formula. When we convert this formula to mole fraction, we can obtain this formula. So these are the all the formulas which are used in solving the many problems, depending on the particular case, whether it may be A through non-diffusing B, whether it may be a equimolar counter diffusion case. So next is the diffusion rates. So how the diffusion takes place, we already know. The when we are just dissolving some dye, dissolving some coloring component, the process which is taking place is nothing but a diffusion. When we are spraying some room freshener around the room, the process which is taking place, for the process which are giving fragrance, which are giving a pleasant odor to us, pleasant smell to us, is nothing but a diffusion process. Okay, when we are spraying some mouth fresheners in our mouth, some asthma patients frequently use this one. So some mouth sprays. Okay, that process is called a diffusion process. Because of diffusion only, all these are getting transferred. Just wait a minute. Okay, yeah. In all this process, diffusion is the main process which is happening here. So the rate of diffusion will depends on the temperature, pressure, and the nature of compositions also, or the matter of composition, or the state of the particular components is also acts as a major criteria in diffusion rates. So how the diffusion rates will be influenced with the temperature, pressure, and orientation of that particular molecules. Then the first orientation is the gases. Okay, the first orientation is the gases, because gases are present. The mean free path is very high. Okay, the distance between particle is very high in the gases, so that diffusion will take place at high rates, very high rates in terms of gases. So the molecular diffusion is dependent on both pressure and temperature in the three cases also. When temperature, we will increase the temperature, the higher the temperature, the rate of diffusion will be very high. Since gases is compressible, higher pressures are very much not required for the diffusion in terms of gases, whereas lower pressures are very much required. When pressure is very low, the diffusion rates will be very high. When liquids also, because compared to gases, the orientation between liquid particles is very less. Okay, uh, uh, very less. As you can see from this example, when we dissolve certain dye or certain pink color into the hot water, the diffusion rate is very high. It is dissolving very easily. Whereas when we dissolving that pink dye or pink color in the cold water, the diffusion rate is very high. Because of the low diffusion rates, the in the cold water, the particular dye is very much less dissolvable. So this is the example that higher temperatures will favor the liquid phase diffusion rates also. At the same time, the liquids in the diffusion rates are very slow compared to the gases. In the liquids is very slow compared to the gases, because in the gases the diffusion rates are very high. The high temperatures are favored in the liquid phase, and at the same time in the gases phase
also, since liquids are not compressible, so pressure is independent, so it cannot be affected, the diffusion rates are not affected. Whereas in solids, because the orientation between particle point orientation sorry, just wait. Yeah, because the orientation between solid particles, individual particles, is very high in the solid particles compared to liquid or gases. So the diffusion rates will be very slow compared to liquids or gases. So in the solids, the diffusion rate is very high. In liquids, the diffusion rate is very moderate. Whereas in gases, the diffusion rate is very high. So solids also incompressible. So pressure could not affect the diffusion rates in the solids, whereas increasing the temperature increases the diffusion rates in that all three orientations, like liquid, gas and temperature. High temperatures are very favored, okay, whereas pressures will not have a effect on the liquid and solid, whereas pressure will have a effect on the gases. So this is the diffusion rates. The next one, how to determine this diffusivity coefficient. So diffusivity coefficient is nothing but DAB, diffusivity of A through B. So how to determine this one? There are two experimental methods to determine this diffusivity coefficient. The first one is the twin bulb method. Second was the Stefan tube method. In the twin bulb method, what will happen? You two
అరే పవర్ కట్ అంటరా సార్ లెఫ్ట్ అయిపోదావా
ఆగాదు, ఇంకా 15 నిమిషాలు ఉన్నాయి.
Thank you, thank you.
Hello.
Sir,
Yeah, am I audible?
yeah, sir,
Yeah,
yeah.
yeah.
Sir, yes, sir.
Okay, okay. Yeah, same one. We will continue the same discussion in the next class. Third class is there, I guess, today. Isaac,
Sir,
please download the attendance. Through mobile, it is not possible to download attendance. I guess. Yeah. You are also a presenter, so you can download this time.
sir, no option is showing, sir, here.
Okay, for you
Option,
also it is not showing. Okay.
yes, sir.
Okay, please take attendance. You are taking some screenshot, huh?
I, sir, will take screenshot, sir.
Right.
Nobody, please don't leave. I am taking attendance, please. Wait.
వచ్చేసి అందరు
Okay, sir, attendance, I took photos of this, sir.
Okay, okay. Thank you. Yeah. Okay, if anybody is having doubt, just ask me. Doubts. Clear the doubts. Okay, in the afternoon session in the third hour, I guess. So in the third hour, I'll check your notes. So please try to solve those problems. Okay, because already all the problems are solved. But once again, if you solve, many doubts will then only you know whether the answers are correct or not. But I just solved in the last semester itself. For your seniors, I've just given that same note. So when you solve those, then you can encounter many of the problems in that one. Whether I don't know that numerical is also correct or not, answer is correct or not, but formulas we can use according to that particular case. We can use the same formulas. So, but answers we need to check once again. So if time permits in the third hour, I will see. If time doesn't permit, then quickly I will go through two to three problems. Okay, that's all. Probably in the next day, next another day, with the mass transfer is there, I will try to start the second unit, which is the distillation, which is very important distillation because there are unit 2 and unit 3 is completely regarding the distillation. In that one, more problems are involved, more the procedure is involved, like McCabe-Thiele method. Okay, McCabe-Thiele method, how to estimate the plates and everything will be. So we need to do much seriously this unit 2 and unit 3. Once we just get down from this unit 1, it's completely over. So please try to solve this, all the problems at the with wetted water, using wetted water. That's a major question. And next one is what is mass transfer coefficient? So mass transfer coefficient, when you derive all the four cases, A through non-diffusing, B equimolar counter diffusion, mass transfer coefficient is nothing but whatever the quantities which are left after considering flux and driving force is called a mass transfer coefficient. Like if you consider Na is equal to dAb by Z, Ca1 minus Ca2. So here there are two quantities according to the mass transfer coefficient definitions. Na is equal to dAb by Z, Ca1 minus Ca2. Ca1 minus Ca2 is a driving force and flux is Na. So whatever the other than the other quantities like dAb by Z is nothing but a mass transfer coefficient. So since Kc, this is a C, concentration, driving force is expressed in concentration, we will consider this dAb by Z as Kc. So mass transfer coefficient when the driving force is expressed as concentration. So that is the Kc case. Those mass transfer coefficients, if you derive those four cases, that mass transfer coefficients are very easy. I don't think last time we tried one problem, okay, CCl4 something. I don't think anybody has given me the answer that one. Anybody solved that answer? Am I audible?
Yeah, sir.
Yeah. What is the answer?
Sir didn't solve it, sir.
Okay, yeah, as usual, expected. Okay, same in the
No,
problem
sir.
handout which I have provided. What? Yes,
No,
Ravi.
sir. On that day itself, I solved up to last step, sir. You said let
Step,
us
but
last
due
steps.
to lack of calcium, I couldn't give the answer.
No, sir. I did all the calculations up to last step, sir. You said let us see in the next hour. I'm leaving now. You were in a hurry on that day.
Okay, okay, yeah, yeah, yeah. Okay, in the given
And
handout,
in the next hour, we started on the topic.
Yeah, yeah. Okay, in the given handout, solid problems. In that one, ninth problem is that same question, CCL4 question. We can go through that one. So the
Yes.
answer will be 6.28 into 10 power 5 something it will get. This 10.5 meter square per second. Okay, ninth problem is that one. The unit one solutions for problems.
Okay, sir.
Solve that for the next class. Okay, so these are very much important. Every problem which I have given in this one is from your old question papers only. Okay, today I will try to give you that old question papers also, whatever I have. I am having that one. So we can go through that one. So every from the old question paper in your notes, unit one notes, and in this problems notes, everything is from old question papers only. Apart from that, I couldn't do anything. Okay, almost every syllabus part is completed, but from your old question paper, there are many questions out of syllabus. Also, two three problems are there. Okay, we need to look into that one also. Okay, try to solve that question and try to write your notes. Okay, notes is compulsory. Without notes, you can't understand. CT2 it is okay. Okay, without notes also you can understand. You can just refer to PPT and go to the exam. But mass transfer one is completely different. Without notes, writing with your own hand, there's no problem in passing this unit mass transfer one course. Okay, just I hope you understood this one. So in the next class, I will just check your notes. Whatever you completed, just show me. Okay. Okay, I'm leaving. You might having the next class also.